Thank you for your introduction. As mentioned, I will tell something about very high cycle fatigue on high-strength steels. I think you all have heard a lot about it during the plenary lectures on Monday and Tuesday by Professor Hong and Professor Stanzelczek. But I will focus on the crack initiation by FGA formation investigated at artificial defects. And now I will tell you something about it and how it can help us to understand the very high cycle fatigue at high-strength steels a little bit better. At first, something you already saw, the high-strength steel show classical fatigue properties. Here's the SM curve for a martensitic and a bainitic state. Martensitic is blue and bainitic in red. It's a classical 100 chromium 6 bearing steel. And we see 3 different stages of fatigue crack initiation. At first we have the crack initiation at the surface with decreasing stress amplitudes. This changes to subsurface initiation with the formation of the so-called fissure fracture surface. It's a very smooth circular surface. And then where our special interest lies on is the very high cycle fatigue, where we see the formation of the fine granular area. It's a very granular area about around the inclusion, and this only forms during very high cycle fatigue. It's also called ODA, as in the presentation by Professor Lang. And if we take a look at the stress intensity factors at the initiating inclusions, we see that the formation of the FGA only starts or occurs if the stress intensity factor at the inclusion is lower than the threshold value for long crack propagation of our material. We calculate this by the formula provided by Professor Murakami. So here you see a surface initiation, subsurface initiation with fissure formation is just above the threshold value for long cracks, and below we have the formation of FGA. If we now calculate the stress intensity factor at the border of the FGA, we see, at the red signs, these are the red signs for all the FGAs we observed. We can see that this value just surpasses again our threshold value for long crack propagation, and so it can be seen as the initiation of a long crack by this FGA formation. If we now take a closer look at the microstructure inside this fine granular area, therefore we performed cross-section cuts with focused ion beam milling. You can see it here. Here's the very rough fracture surface in the FGA. And if we now take a closer look by transmission electron microscopy, and there with selected area diffraction, we can see, because of the ring-like structure, we have a polycrystalline structure along the fracture surface with a strong grain refinement along the fracture surface with grains much smaller than 100 nanometers. Just short below it, we have the original microstructure of our material. It's much coarser, even if it's still fine. It's a martensitic structure, and that shows. Here you see the Lauer pattern from the diffraction, and that's just 1 or 2 grains in this case. And so we know it's a thin film of about smaller than 0.5 micrometers. Where this grain refinement takes place at the fracture surface. But that's all things that were shown in the plenary lectures, and there exist a lot of mechanisms which shall explain how this fine granular area forms. But we all have to deal with the problem. We have our own model too. I won't show it today. I think 2 different models for this during this conference is enough. But we have all to deal with the problem that we can't in situ detect the failure, and we can't predict where it happens. So we only see the final fracture surface, and we can only guess how it had happened because we just see the result but cannot detect how it really forms. So we want to make it observable by putting the failure to the surface. So we insert artificial defects in the surface of our specimens. Here you can see one in the cross-section cut. It's a focused ion beam cut, a V-shaped cut in our material. By inducing these artificial defects, we can define the point of crack initiation, and by the size of the defect and the applied stress, we can also define our stress intensity factor. That gives us good options for the testing. If we now perform these tests in ultra-high vacuum, we can simulate the conditions we have in subsurface failure, and by this simulate the failure mechanisms we observe at subsurface failure. I will show you this in detail now. We perform our tests with the ultrasonic testing device below here. You've seen that a lot even today. It's a stress ratio -1, frequency of 20 kilohertz. We test until 10 to 9 cycles. We allow a maximum temperature increase of 15 Kelvin. Therefore, the system is air-cooled. We test in pulse pulse mode. So we have effective frequency of 1250 Hertz. And the artificial defects are put in the center of our specimen. The specimen's up here. And here's a surface, a view from the surface. It's just a V-shaped cut in our surface. And here's a cross-section cut. It's a rectangular shape. And if we have the square root area parameter for the Murakami equation, it's in our case 17 to 20 micrometers for these defects. Below here you see a cross-section cut through our vacuum chamber, where we can test with a pressure below 10 to -6 millibar. So now the material, 100 chromium-6 in a martensitic condition. Here you can see the microstructure. I won't take too much time for this. I think everyone knows the material. Here now to our fatigue results. This is the SN curve for the tests with artificial defects. We performed the most tests in vacuum. These are the black signs. But we performed, for comparison, a few in air until now. What we at first can see, in this case, we don't have a change to subsurface failure, but we have very high cycle fatigue at the artificial defects. If we have a short lifetime, you can see it for this specimen. It's a very smooth fracture surface, just like fisheye. But if we have very high cycle fatigue, you can see it at this. We have the fine granular area around the defect. It's quite good to see. But you can see also at the tests in air, at this stress level, we just have runouts. So it seems, as reported in literature, that vacuum is a necessary condition for very high cycle fatigue with FGA formation. So now to the fracture mechanics, just as for inclusions. We see that the high cycle fatigue with fisheye formation occurs if the threshold value for long cracks is overrun, but if the stress intensity factor at the defects is below than the threshold value, we get FGA formation like this. If we now evaluate all our FGAs we observed, with stress intensity factor at the border, you can see that it just overruns our threshold value for long crack propagation, just like for inclusions, and then initiates a crack in the fisheye. I also have to mention for surface defects, we take the equation for surface defects Murakami provided. So it's just the same for the artificial defects. The FGA formation ends for Kmax FGA larger than the threshold value. Now to the one thing I want to mention: these two runouts in vacuum showed cracks, but they didn't lead to failure until our ultimate number of cycles. These two signs are the stress intensity factors for these cracks if we assume they are circular, and you can see they just might have been short before failure. And you also can see, we now can see cracks in the very high cycle fatigue regime before failure. That was not possible before. So now to the microstructure, we have to check if it's also the same for the artificial defects. Here is fisheye without FGA for a short lifetime, comparatively short. We have a very smooth fracture surface. Here is the defect. The propagation is in this direction. It's very smooth, nearly no crack deflection. And if we perform the selective area diffraction, we also see there's no grain refinement. But if we now take a look at a FGA, a focused ion beam defect, we see here's also the defect and the propagation to the right. We see that the fracture surface is much rougher. And if we perform the selective area diffraction along the fracture surface, you see the ring-like structures and there's clear grain refinement, just like for failure at inclusions. Short below, this grain refinement is not detectable, so it's just, again, like at inclusions, a very thin layer of microstructural change. This fine grains consist of martensite, just like it is also at inclusions. And further we can see the transition from FGA propagation to fisheye propagation at this point. From here on we have no more grain refinement, and this the value, if we measure it, is just like we would have assumed from the SEM pictures by the roughness of the surface. That fits quite good. So if we take a closer look to the fracture surface, you can see here it's a border of the fine granular to the coarse granular to our original microstructure, but it's not always good to see because the transition is more smooth. It's not a harsh cut between the small grains and the large grains. You also can see by the bright parts here that there are some micro cracks inside the FGA. Also here some bigger micro cracks. But that's also things we can see at FGAs at inclusions. So let me short summarize my talk. We can perform or we can reproduce the very high cycle fatigue with FGA formation at artificial defects if the tests are performed in ultra high vacuum. The fracture mechanical and the microstructural observations correlate quite good with the observations we had in inclusions, and this gives us quite some new methods to observe the failure before final fracture, and hopefully we can get by this pre-stages of failure and understand the formation mechanism a little bit better than just by looking at the fracture surface. Below here, sadly we couldn't perform the TEM measurements till today. You see the tip of our defect with a very small crack that we observed after 10 to 9 cycles. And I think this is also because of the roughness, this is a FGA crack we can look at even before the crack tip, so maybe we can see which mechanisms are responsible for the formation of this fine granular layer. And this will give us a deeper insight into very high cycle crack initiation. Thank you for your attention.